Hi, I'm Reverend Greg and I welcome you to this tutorial series about GLSL shaders for hobby programmers in GameMaker Studio. This first video is an introduction to GLSL and will explain how GLSL works, but does not show how to implement a shader in GameMaker Studio. It will take some time to explain all the basics, so this video is probably going to be quite long, but I think it's extremely important to know those basics before we start to code some shaders. Disclaimer, I'm quite new to shaders myself, and programming and math stuff is not what I learned professionally, so I'm actually not super qualified to do a series on shaders. But I failed finding a good introduction series suitable for hobby programmers, and thus spent a lot of time watching videos and reading stuff which usually explained only the first few steps or were quickly getting too complicated for me. So I also tested and experimented a lot and would like to share what I learned so far in a more guided way. In the description below I linked to some sites and videos that helped me learn and might help you too. One is GM Wolf's Introduction to Shaders, which is a really good introduction really. And one is Source Tutorial Blog, which is great really, but might go into depth too quickly for some people. Another great tutorial is Matt Delaurier's GLSL tutorials on GitHub. And I also watched Virtual Studio 3D Shader Dev tutorial series on YouTube, although they got too complicated quite quickly, at least for me. And then of course there's Shaun Spaldings YouTube tutorials. He has a nice short introduction and a really cool outline shader. And I also learned from a library by Chansik on GitHub. And I sometimes also asked for and got help on the GameMaker forums. Really thanks to Flying Saucer Invasion and Fel666 for their help on shader-related problems there. Target audience are people who know at least a little bit about programming in GameMaker Studio and feel like they're missing basic knowledge about shaders. Also, I'm only focusing on stuff for 2D games since that's the strength of GMS, and frankly I don't know anything about 3D games in GMS anyways. And since I want to target on different platforms, I will only discuss OpenGLSL shaders. But as far as I can tell, what you learn in GLSL will help in HLSL as well. To follow this tutorial series, you need some basic understanding of GMS and its scripting language. I will be using GMS too, but all the shader code and nearly all GMS code will work in GameMaker Studio 1.2 or new as well. It will help quite a bit if you try to understand a few shaders already, but it's okay if you fail so far. Hopefully this tutorial series will help you with that. However, you don't need any knowledge of GLSL and you don't need to be a maths crack, because I sure ain't anyways. Everyone who knows a lot about shaders will most likely be bored, because after this primer video we'll progress quite slowly and exercising with several simple shaders before moving on to the next level. And everyone who's good at maths will probably either laugh or cry sometimes watching this series, because you might encounter situations where you see a better mathematical solution than me. But that said, if you notice something I tell is wrong, or if you have a good idea on how to improve what I show, then please tell me in the comments. If there's enough input, I'll add a video to show those corrections and improvements for all viewers to learn from my mistakes. Most of these shaders will be post-processing shaders, meaning they make most sense to apply to the whole application surface. However, some are or can be used as effects on single sprites or smaller surfaces. Now about shaders. Shader are programs running on the graphics card or GPU and determine how 3D objects are drawn to the render targets. Those render targets are actually just surfaces, like in example the application surface. Eventually, somewhere at the end of each frame, GMS will send the application surface to the GPU again, but this time the GPU will draw the application surface to the screen instead of another surface. Since we can program a shader and thus how everything is drawn, we can use that to create effects, changing colors or the position of each pixel we draw. Now you wonder, why 3D objects? Didn't you just claim this series is about 2D games? Well, when it comes to shaders, a sprite is basically a 3D model of two triangles forming a rectangle with the sprite as a texture glued to it. So to understand this, we need to understand a little bit about 3D models and textures. A 3D model on a basic level is made of points in space connected with lines. Those points are called vertex or vertices in plural, and together they give shape to the model. Vertices don't just contain positional information, however. They can also have a color and thus colorize the model. To make that color look more interesting, an image can be glued to the surface of the model. Those images are called textures. And the main purpose of a texture is just that, coloring the model. But additional textures can also be used as instructions to change the color of the base texture. In example, a bump texture, also called a bump map, is used to change the behavior of light on the surface of the model, and that makes the surface look like it had a relief. One thing about textures will also be very important. Sprites are stored on a texture page. GMS automatically creates enough texture pages to have every sprite somewhere on one of those. Under Options, Windows, Graphics, you can actually get a preview of how the texture pages currently look. Here you can see a sprite and the texture page it is on. You can tell GMS to put a sprite on its own texture page, but the default is that GMS tries to put as many sprites on one texture page as possible. And that makes sense because swapping a texture page on the graphics card takes time, and if many sprites are drawn on the same texture page, then the graphic card doesn't need to load new textures as often as if every sprite was on its own texture page. So that's texture pages. As just said, vertices store their position in space and their color values. Another important piece of information they store are their position on a texture page, so the GPU knows which part of the texture page to draw, the part with the sprite on it. So in our texture page example, the vertices of the red car sprite also store the coordinates of that red car sprite on this texture page. Now back to the sprite in GMS. When you tell GameMaker Studio to draw a sprite, GMS creates a plane with 4 vertices as the corner of the plane. Then GMS sends that plane with its vertices and the texture page the sprite is on to the GPU, and the GPU draws that to the render target. To do that, the GPU has several shaders like vertex shader, geometry shader, fragment shader, also called pixel shader, and compute shader. The geometry shader and the compute shader cannot be used in GMS, so this series will only deal with the vertex and the fragment shader. And actually, mainly the fragment shader, which certainly is the most important in 2D games, although we will look at the vertex shader as well. Those shaders, with the exception of the compute shader, are working in a pipeline. Each shader has inputs, calculates its stuff, and passes the output to the next step in the pipeline. The first shader in the pipeline is the vertex shader. As explained before, GMS sends the sprite together with a plane and its vertices to the GPU. The vertices are then sent to the vertex shader with their vertex data, like in example position in space, vertex color, and coordinates on the texture page. The vertex shader processes that data and passes the processed information on to the geometry shader. The code inside the vertex shader is run once per vertex of the object, so 4 times per sprite since the sprite is on a rectangular plane, and it needs to do that for each sprite or surface once per frame of the game. The second shader is the geometry shader. It deals with the 3D object data as whole instead of on a per vertex basis like the vertex shader did, but I can't tell you more about the geometry shader, and we can't use it in GMS anyways. The next few steps are clipping and transformation stuff I can't say anything about either. After those mysterious steps, everything needs to be rasterized and is passed on to the Fragment Shader. The Fragment Shader's job is to transform the data into pixel information. Here is calculated what pixel gets what color. The Fragment Shader receives the vertex position, the vertex color, the texture coordinates of the vertices, and the actual texture. But we can also send additional textures directly into the Fragment Shader and mix those in to calculate the final color. The Fragment Shader runs once per pixel of the sprite or surface. So for a 64 pixel by 64 pixel sprite drawn one-to-one to the screen, this means the code runs 4096 times. For a post-processing effect of a full HD game, it runs 1920 times 1080, which is a bit more than 2 million times per frame. This shows that optimizing a complicated Fragment Shader can make quite a difference, especially on slower devices. The reason why the GPU can handle that huge amount of calculations is mainly because the GPU, unlike the CPU, can do lots of those calculations simultaneously and is built to do the implemented operations really fast. The Fragment Shader outputs the color of each pixel to the next stages of the GPU pipeline. Most interesting to us is probably the blending stage, where the color from the Fragment Shader is blended with the color of whatever the pixel is drawn upon. In example, the application surface. We can't write programs for the blending stage, but we can tell the GPU how to blend using blend modes in GMS. Now let's have a closer look at shader programs. If you haven't ever looked at a shader before, you might first continue with the video where I show the first few very simple shaders, because now I'm explaining a lot of stuff in the vertex shader and fragment shader, and I think it really helps to have looked at some examples before continuing with this video. This is a pass-through vertex shader. Pass-through, by the way, means that the shader is just calculating what the next stages in the GPU pipeline need without doing anything else to that data. Right away we see three parts: the attributes, the varings, and the main function. The attributes contain the vertex data and are passed from GMS to the vertex shaders. The attributes are in position. A three-dimensional vector, it's the position of the vertex in room space. In normal is a three-dimensional vector describing the vertex's normal vector. It's only used on 3D objects. The in color, a four-dimensional vector, is describing the vertex's color in red, green, blue, and alpha. And the in texture chord is a two-dimensional vector describing the vertex's position on a texture page. We cannot change the content of those attributes, but we can process them and store them in new variables. So in example, we cannot write in position equals something, because we cannot change an attribute. But we can write something equals in position and then change that new variable. Varying are variables that are passed from shader to shader. In this case, the two varying, the varying vector text chord and the varying vector color, will be passed from the vertex shader to the fragment shader. We'll see the same varying there again when we get there. Between the attribute or varying and the actual variable name, we also see vec2, vec3, and vec4. These are the data types of the variables, telling what type of data the variable holds. Declaring the data type of each variable is mandatory in GLSL. If a variable data type is not declared, the shader won't compile. In GameMaker Studio we don't use data types, so this could be a bit confusing at first, but it's actually very simple. But let's just get an overview of the most important data types in GLSL. The first data type is int. Int is an integer. It can only store whole numbers and it mustn't ever be written with a decimal point. So this will work. Int I equals 1. But this will throw an error. Int I equals 1.0. Also very important, GLSL needs you to tell where the end of an instruction is. So the semicolon at the end of each instruction is mandatory. The next data type is float. Float are real numbers. Floats need to be written with a decimal point, so this will throw an error. Float factor equals 1, because it tries to store an integer in a float variable. But these will work. Float factor equals 1.5, or factor equals 1 dot, or factor equals 0.5. Also note here that I didn't declare the data types more than once. Doing so would throw an error too. So this would work. Float factor if varying vector text code is greater than 0.5, factor equals 0.0, else factor equals 1.0. However, this wouldn't. If varying vector text code is greater than 0.5, float factor equals 0.0, else float factor equals 1.0. This won't work because the variable factor can only be declared once in the whole code. The next data types are vectors. Vec2, Vec3, Vec4 are vectors with a different amount of components. A vector stores multiple floats similar to a one-dimensional array. A vector 2 stores 2 floats, a vector 3 stores 3 floats, and a vector 4 stores 4 floats. They're always floats. Vectors need to be constructed. We'll look into that in detail later, but inside the pass-through shader, we already see such a construction. Vector 4 object space pass equals vector 4 in position x, in position y, in position z 1.0. First, a new variable called object space pass is declared as a vector 4 data type. As we've seen before with the int and float, GLSL expects to get the same data type, in this case a vector 4, on the right side of the equal sign as well. But the 4 values on the right side are 4 floats, in position x, y, z, and 1.0 are all floats. To create a vec4 from those 4 floats, this code wraps those 4 floats in brackets and adds the constructor vec4 in front of the brackets. This constructs a vec4 from 4 floats. But as I said, we'll see more about constructors later on. There are more data types, but these are the most important ones. We'll look at one more inside the Fragment Shader though. Aside from attributes and varyings, there's also another important type of variables, the uniforms. With those variables, we can send information from GameMaker Studio into the shader. The difference to attributes is that we cannot control the attributes. That's handled by the engine, but we can decide what information the uniforms send into the shader. Every shader, except I think one, we will create in this tutorial series will have at least one uniform. However, attributes and uniforms share some similarities. One is that we cannot change a uniform within the shader. So we cannot write uniform float brightness times equals 1.1, because we cannot change the uniform brightness. Another similarity is uniforms like attributes can only be used in the shader where they are declared. uniforms cannot be passed on from the vertex shader to the fragment shader, but both can have their own uniform. And of course we can do something with a uniform in the vertex shader, store the result in a varying and pass that varying on to the fragment shader. A last type of variables aside from attributes, varyings and uniforms will encounter are constants. They're pretty much the same as in any other language and can be set like this. Const float factor equals 0.5. The third big part of the pass-through shader is the main function. Many programming languages need a main function. It's basically the code that runs when the program starts. But what confused me was the word void in front of main. Now, everyone who knows some other programming language than TMS probably won't be confused by that at all, but I was, so let me explain what that void means. In GLSL, every function needs a return data type. So in example, if you write a function that returns a float, you need to declare the return type float before the function's name, just like so. vec3, calculate contrast, vec3 call, float strength. vec3 new color equals something, return new color. So this function returns new color, which is a vec3. So the function must be declared as vec3 as well. I won't explain more about functions here because they're pretty easy to use, but we might encounter one or two in the tutorials. The reason why I mention all this is that I had trouble understanding why the main function always had a void in front. The reason is really simple though. Every function, including the main function, needs to be declared with a data type, even if it's not returning anything at all. Void preceding the function name just tells GLSL this function won't return anything. Let's see what happens inside the main function. Here we first see a line we already looked at before. vec4 object space pos equals vec4 in position x, in position y, in position z 1.0. This line gets the object space position of the vertex the shader currently is calculating. It's getting that information from the vertex attribute in position and adds a fourth float 1.0 to complete the vec4. That 1.0, as far as I know, is needed to transform the vector by a 4x4 transformation matrix, but I'm not sure about that. But the transformation is exactly what happens in the next line. GL position equals GM matrices, matrix worldview projection times object space position. Object space pos, just created a line earlier, is now transformed by a 4x4 transformation matrix called matrix worldview projection. In other engines, programmers need to write that matrix themselves. In TMS, this matrix is built in. The newly transformed vector is then stored in the GLSL built-in vec4 variable GL position. GL position is the main output of the vertex shader, and it is passed on in the GPU pipeline. So every vertex shader will need to set GL position somewhere. Beneath that we see the two varyings that were declared above the main function. Varying vector color stores the vertex's color to pass it on to the fragment shader. To understand what this does, we can have a look at the GMS function drawSpriteGeneral. drawSpriteGeneral, sprite, subimage, left, top, width, height, x, y, x scale, y scale, rot, then color 1, color 2, color 3, color 4, and alpha. drawSpriteGeneral gives the 4 vertices of the sprite a color, the vertex color. That color is stored in the attribute inColor of each vertex. Now here it gets a bit complicated. In the vertex shader, the variable varying vector color is a varying, but it will not just pass the vertex color onto the fragment shader. It will pass the interpolated color of a fragment or pixel between the vertices. As you can see in the 4 colors spread out from the 4 vertices of the sprite, the vertex shader interpolates the 4 colors we set in Draw Sprites General, passes that interpolated value for each fragment or pixel to the fragment shader, and the fragment shader blends the color with the sprite's texture color. As a side note, this example also shows if you don't need the vertex color in your rendering, you won't need the attribute inColor or the varying VV color inside the shader. You can then just remove these here. Just don't forget to remove the varying color from the fragment shader as well, or every pixel will be multiplied by 0, resulting in a black rectangle. Varying vector text code is doing a similar thing with the texture coordinates of the vertex. It stores the interpolated texture coordinates of a specific fragment or pixel on the texture page and passes that data onto the fragment shader. This is needed because when drawing a sprite or surface, the fragment shader needs to know where to find those pixels to draw. It gets a texture page and coordinates of where on that texture page the sprite is located, and then renders those pixels. Let's have a look at a sprite and the texture page the sprite is on again. You see the sprite is here on the texture page. The coordinates of the texture page always range from 0 to 1. 0, 0 is the upper left corner and 1, 1 the lower right. So this sprite will have coordinates of 0.5, 0.6, and 0.76, 0.73. The texture page won't always be the same size. In example, if you set the sprite to have its own texture page, that page will have the same size as the sprite. So the sprite's coordinates on the texture page will range from 0, 0 to 1, 1. The same goes for surfaces. Their coordinates also always range from 0, 0 to 1, 1. But as soon as the sprite is on a mixed texture page, its coordinates will hardly ever be 0, 0, 1, 1. And that's really important to remember. So this pass-through shader is doing nothing else but setting up later stages in the GPU pipeline. The vertex shader, however, could, in example, change the position of the vertex, or change the vertex color, or prepare texture coordinates for a second texture passed to the fragment shader. It can most likely do much more, and I just don't know about it. Now let's have a closer look at the fragment shader. The fragment shader is often called pixel shader as well, and although I usually call it fragment shader, if you think of it as a pixel shader, it will probably be easier to understand. Where the vertex shader dealt with vertices of the sprite, the pixel shader will deal with the pixels to be drawn. The fragment pass-through shader looks a lot simpler than the vertex pass-through shader we just looked at. The first thing to note are the 2 varyings, the varying vector text chord and the varying vector color. At the vertex shader, I told you we'll meet those again, and here they are. Since varying are passed on from shader to shader, every varying variable needs to be declared in both shaders, or the vertex shader cannot pass them on to the fragment shader. Inside the main function, the pass-through shader only has one line of code. GLFrag color equals varying vector color times texture 2D GM-base texture varying vector text chord. GLFrag color is the output of the fragment shader. At the end of each fragment shader, we need to set it to something, or the shader draws just black pixels. GLFrag color is a vec4 data type, so we also need to make sure there's a vec4 on the right side of the equal sign. Varying vector color is a vec4. It contains the interpolated vertex color we received from the vertex shader. If one vertex has the color red and the other is yellow, the fragment or pixel halfway between will be interpolated to orange. So VV color is not red or yellow at that point. VV color is orange. GM base texture is of the data type sampler 2D. So it's a texture, and it's simply the texture of the sprite or surface you're drawing with GMS functions like drawSprite or drawSurface. I'll explain a little bit more on the data type sampler 2D in a few seconds. GM base texture is a built-in variable for GameMaker Studio only. You will find something similar in any fragment shader in any language, although in many cases more complicated than this. Varying vector text code is the interpolated texture coordinate of the texture page we are drawing. Again, we're not drawing vertices here, we're drawing a specific color from the texture between those vertices. So VV text code is not the texture coordinate of the vertex, it's the texture coordinate of the fragment or pixel between the vertices. The last thing we need to look at is the function texture2D. What this does is take a texture that's GM base texture here and coordinates on that texture and returns the vec4 color of that pixel on that texture. So here we are, the vec4 with the texel color is multiplied with the vec4 of the interpolated vertex color, and the result is stored in the built-in variable GLFragColor, which the GPU will pass on to the next stages for each pixel drawn. For each pixel on every frame, 60 frames per second. That's pretty impressive and still blows my mind. I also mentioned earlier that we'll see the last really important data type. It's not used in a pass-through shader though. The data type is called sampler2D and actually just holds another texture. So if we need an example, a bump map like I showed way in the beginning with the brick wall sphere, we can pass that bump map texture to the fragment shader, and the variable holding the texture is of that data type sampler2D. As mentioned, the built-in variable GM base texture is of that data type sampler2D. We will work on some shaders using sampler2D, but the first few will do without. There are several more stages after the fragment shader, but I actually can't tell you anything about them except for the alpha testing and blending. The alpha testing is pretty much just a stage where pixels with an alpha lower than a threshold get discarded. You can read more about it in the GMS documentation if you want to, but I'll never before use that functionality. The blending stage, however, can be really important. I already mentioned that in the end, all that stuff calculated in the shaders will be drawn to the render target. Some surface, like the application surface or just an effect surface you want to process further. Up until to this point, the GPU has no clue what colors are on the render target. In the blending stage, however, the GPU blends the source pixel, which was just calculated in all those pipeline stages before, and blends it with the destination pixel of the surface we're drawing upon. How this is done seems to be really confusing to many GMS users, because originally opaque pixels on the destination surface can suddenly become transparent. Why this happens is very well explained by Mark Alexanders in a tech blog on the GameMaker page. The blog is called Explaining Blend Modes Part 1 and Part 2. I can only recommend reading that blog if you haven't done so already. I will come back to this topic in a much later video after we already covered several basic shaders. This video is getting really long already, and so I'm going to make a cut here and we'll see the last part of this introduction in the next video.